Okay, so now we're going to talk about the last kind of stage of a titration, and that is when our sodium hydroxide has reacted with all of the acid, the weak acid that's present, right? So if we have an equal amount of sodium hydroxide as we do acid, all the acid will react and there will be no more weak acid present. Now you'll recall from the strong acids and strong bases that when the amount of sodium hydroxide equaled the amount of acid that was present, we reached the equivalence point, right? Where the amount of H plus was equal to the amount of OH minus, and they both were at 10 to the negative 7th molar, basically, which gave us a pH of 7. Now, in weak acid titrations, it's not that simple. The answer is not always 7 at the equivalence point. And we'll talk about why that is, and that's kind of basically the thrust of this. This is probably the most complicated uh, of these calculations that we're going to have to do, but it's important because the equivalence point is how you're going to know how much of your acid you have present, right? So let's get into it. We'll see how it goes. Okay, so we have been working with 100 milliliters of a 0.7 molar acetic acid solution. And now we're looking at what happens. So this is equal to 0.07 moles, right? 0.7 times 0.1 liters gives us 0.07 moles. Now we're going to look at what happens when we add 46.67 milliliters of 1.5 molar sodium hydroxide. Because if we take these two numbers times each other, we get 0.07 moles. Okay. Now, if you're good at doing ice tables in your head, you have probably already figured out where this is going. But if you're not doing ice tables in your head, that's okay too. This is why we write them out, right? So the ice table here is acetic acid is the initial concentration is 0.07 moles. The initial concentration of sodium hydroxide is also 0.07 moles, and the initial concentration of conjugate base is 0. Now we know that we need to get to 0 for the sodium hydroxide. All of the sodium hydroxide is going to react. So we subtract 0.07 moles from 0.07 moles, and we get 0. And now, since we know the change, we know that all the other components of this reaction will also change by 0.07 moles. And so we're going to be able to fill in the rest of our ice table with those numbers. And of course, what we're going to see is that we have no acid and we have no sodium hydroxide remaining. It has all been converted to the conjugate base and water. So at this point, if this was a buffer, we would apply the Henderson-Hasselbalch equation. But of course, because there is no acid concentration, this is not a buffer, right? And so in this case, that means that the Henderson-Hasselbalch equation can't help us. The Henderson-Hasselbalch equation does not apply to this situation. And if you try to plug in these numbers, what you'll find is that when you go to put in the acid term in the Henderson-Hasselbalch equation, right, the log of base over acid, if the acid term is 0, then you're dividing by 0 and bad things are going to happen, right? So mathematically, at least, you'll probably be fine. But because we're not dealing with a buffer, we cannot use the Henderson-Hasselbalch equation. And so when we reach the equivalence point, so first of all, let's define the equivalence point. The equivalence point is where the amount of sodium hydroxide, and when we say amount, we're talking about moles, is equal to the amount of weak acid. I should have said strong base. Oh, gosh, I can't talk and write at the same time. I should have said strong base here, right? Because we'll usually be using sodium hydroxide, and in this case we definitely are, but it could be another strong base. The amount of strong base is equal to the amount of weak acid, right? So when we have an equal number of moles of strong base as we do weak acid, then we've reached the equivalence point. At the equivalence point, we must use Kb to find the pH, right? So we really haven't used Kb very much up until this point, and now we get our chance. Okay, so how does this go, right? So first of all, we need to remember what Kb is. Kb is the opposite of Ka, so instead of finding H plus, we're finding the concentration of OH minus, conjugate acid, all over the concentration of the base. The other thing that we know is that Ka times Kb equals Kw, right? So if we know Ka and Kw, we can figure out Kb, right? If we take the negative log of both sides, we know that pKa plus pKb equals 14, which is the negative log of Kw, right? So pKa plus pKb equals 14, so we know the pKa of acetic acid, 4.74. And so we can solve this for pKb. This equals 9.26, which means that the Kb is equal to 10 to the negative 9.26 power, right? So I lost it. This is one of those things that, like, if you write out every step of finding the Kb, it gets to be kind of annoying because you have to like set up the equation, do the subtraction, and all this other stuff. But really, all you're doing is taking 14 minus the pKa. That gives you the pKb, and then take that, put that in the exponent of 10, like this, and you're there, right? So if you know the pKa is 4.74, you can very quickly just take 14 minus that number, and then 10 to the negative that resulting number. So 10 to the negative 14 minus 4.74. That's your Kb. Great. We can put that number in. Right here, 10 to the negative 9.26. And that equals the concentration of OH minus and the concentration of the conjugate acid are, of course, the same because this is a Kb, right? And so we're going to assume that these are the same, and then, or we know that they're the same because that's the chemical equation that we have. And then the concentration of the base is what we have to put down here. Now, the concentration of the base is 0.07 moles divided by the volume of the solution. And so the volume of the solution is these two things added together. So we're going to convert that to liters right there. Right, so 0.07 moles divided by 0.14667 liters. We divide that out and we get 0.477 molar. Right, so this is why the equivalence point is kind of a bear to calculate, because we've been ignoring the volume for most of the time, but now we have to use these volumes in order to get our concentration of the base, right? We know how many moles we have, but we need it to be in molarity in order to make sense of everything else. Okay, 0.477. Solve for x. X equals 1.62 times 10 to the negative fifth. Right, so this is the concentration of OH minus. Now we need to find pH from that. So I usually find the pOH, which is of course the negative log of the concentration of OH minus. If you plug that in, you get 4.79. And then the pH is of course 14 minus that number, 4.79 equals 9.21. That was a lot of calculation, right? It's a lot of calculation to get to one number. Let's go through, I'm just going to walk through the steps one more time. I'm not going to do new numbers or anything, but I want to kind of point out where all these things go. And also, once you feel comfortable with this, where are the steps that you can kind of skip over and just kind of, know what you're getting into. All right, so first of all, we have to be at the equivalence point, right? So when the amount of strong base equals the amount of weak acid. So calculate these numbers out. If you see that these two numbers are the same, you can kind of skip the ice table, right? The ice table is, all the ice table is telling you is that everything is a conjugate base now, which makes sense. So this amount becomes the amount of conjugate base that's present. And then, so you have the amount of conjugate base, you have your volume, you can calculate the concentration of the conjugate base and plug that into the Kb formula. Once you do that, now you have your concentration of OH minus, and you need to convert that to pH, right? You can find the POH first and then subtract 14, or you can divide this, take Kw divided by this number and give you the concentration of H plus, and then take the negative log and get pH, either way, right? But I did a little bit of extra work to kind of show you where all these things fit together, right? And also to get to this final conclusion, which is that the pH of this solution, when we add an equal amount of strong base as we have weak acid, the pH is not 7. The equivalence point for weak acid titrations is never 7. It's always going to be more basic. And the reason for that is that the conjugate base has an effect on the pH, because the conjugate base increases the concentration of OH minus. Right? So because we're talking about weak acids, we have an appreciable amount of OH minus in solution once that weak acid is titrated, which means that our pH at the equivalence point is not 7. So if we were to draw a titration curve for a generic kind of weak acid titration, this is amount of strong base added. Okay, so in this case, we started at about pH 2.4, right? And then our pKa was at 4.74. And then here's neutral, 7. And then here is our final pH, which is about 9.2 at the equivalence point, right? So I'm going to say that our equivalence point is here. Right? And remember that that is where the moles of strong base equals the moles of weak acid. Right? So we're starting here. We have to go through 4.74 at some point, and then we're going to get to here. Now, where does our line cross 4.74? If this is our equivalence point, it turns out that exactly halfway between no base, right? So 0 base added, and what was this? This was 46.67 milliliters of 1.5 molar NaOH, right? Exactly halfway between, so 23.33 milliliters of 1.5 molar NaOH. Exactly halfway is where we're going to hit 4.74, right? So this is always true. So halfway to the equivalence point is where the pH equals the pKa of your acid. And so what this is going to look like is this is going to go up. Oh gosh, that's awful. That's not what that looks like at all. This is going to go up, and then here it's going to be a buffer for a while, and then it's going to go up to here. And then once you get past here, you're just adding more sodium hydroxide, so it keeps going way up like that. But this zone right here, we talked about this a little bit in class on Friday, right? This is where you have a good buffer because the pH is very near to the pKa. And so the pH doesn't change very much in this buffer zone, but once you get out of that buffer zone, right, then you're kind of taking everything over and creating a much more basic solution. So really there's 2 points that we need to be aware of. One is the equivalence point, and one is right here where the pH equals the pKa. Right? And the relationship between them is it takes double the volume to get from 0 to the equivalence point as it does to get from 0 to the point where the pH equals the pKa. All right, so that does it. That is all the calculations that you're going to need to do for the titration of a weak acid with a strong base. I don't have any more notes. So I don't even know how many videos I've done. It feels like I've been doing this all afternoon. So it's a lot. There's a lot of math. There are a couple of good practice, or I hope they're good. There's a couple of practice worksheets that I have developed that I think are good. Hopefully you enjoy them. But it'll do a lot of calculation in there. You'll get to kind of work through these things and recognize that. The thing that I want you to remember is when to use Ka when you have only acid, when to use the Henderson-Hasselbalch equation, anytime you have a mixture of acid and base, and when to use Kb, which is the equivalence point, right? So if you can remember those things, then it's just applying that and doing the algebra and figuring it all out from there. So practice those worksheets. I will link them, of course, on D2L, and you will get good at them. And then we'll be good to go for exam number 3, which comes at the end of this week. So if you have questions, of course, please don't hesitate to contact me, sign up for office hours, all the other good stuff. Otherwise, enjoy your week.